Hi, welcome to our new unit, Unit 7. We're going to be talking about mostly quadrilaterals, but we're going to start with a foundation in polygons. Remember, a polygon is a closed plane figure with 3 or more segments. Remember, when we say closed, that means nothing is open, right? So all my corners touch each other and they make vertices. When we say it's a plane figure, that means it's flat, so it's not three-dimensional. And then it has to have 3 or more segments, so there's no curves allowed because it has to be made with segments. So all of these things are important. The fact that it's made with segments, the fact that it is flat, and the fact that it is what we call closed. There's no openings or gaps in the sides. We have 2 types of polygons that we're going to talk about today. We're going to talk about convex polygons, and that's a polygon where all of our vertices point outwards. So if you think about like a standard regular pentagon, for example, or a trapezoid or something, all my corners are pushing outwards. So this would be considered a convex polygon. All my corners point outwards. We also have what are called concave polygons, and that's where 1 or more vertex points inward. So if you were to think about, for example, like a star, all my corners are going, or all my sides are going to be straight. Pretend I can draw a star, okay? But we can see that, yes, although some of them point outwards, we also have some of our corners that point inwards. If you have at least one corner, it only takes one, if you have one corner that points inwards, then you are concave. And sometimes what I remember is that it is caved in. And that helps me to remember concave, we're caved in, as opposed to convex, where everything's going to be pushing out. So when I look at the next 4, let's take a moment to decide whether or not these are polygons, and if they are they convex or are they concave? So when I look at my first one, is it closed? Yes. There's no gaps in my sides. Is it flat? Yes, it is. And is it made all with segments? Yes. So we're going to say yes. This is indeed a polygon, and then do all my corners point outwards? Yes, they do. So this is yes, and it is convex. Okay? When I look at number 2, or not number 2, but the second image, and I decide, is this a polygon? Is it closed? Yes, there are no gaps. Is it plane? Yes, it's flat. And is it made with 3 or more segments? And because it has to be made with segments, on this one I'm going to say no, this is not a polygon because it has curves, right? And so we can't have any curved edges because then we're no longer made with segments. Okay? Let's look at the next one. On my third image there, kind of looks like a large plus sign that's got really wide edges. It is closed. It has no gaps in the sides. It is flat, so it's plain, and it is made with all segments, so we're going to say yes. This is a polygon, and I can see I do have at least one. There's actually 4 corners that push in, so this is concave because I have some corners that are caved in. And then the last one that I have here, this image that I have, it fails immediately, right? Because it has to be closed, and I can see I have this opening right here. So we're going to say no because it is not closed. I can't have like a way, it needs to be like fenced in, right? It can't have an opening in the sides. So that one is not, these 2 are not polygons. And this one, these 2 are polygons. One is convex and one is concave. Okay? And then the next thing we're going to talk about in this first video is classifying polygons. We've done this before, but it's been a while, so we just want to review. There are some that are tried and true. We for sure know because we use them all the time. For example, when I say what has 3 sides, we're really good at going, oh, that's a triangle. Sometimes if you're just asked what has 4 sides, we tend to want to say square. But we have to remember we have to be less specific unless we're given more information. So if we have 4 sides and that's all the information we have, we're going to call it a quadrilateral. We should know that 5 sides have a pentagon. 6 sides are a hexagon. This one tends to get forgotten about, but 7 sides is a heptagon. 8 sides is an octagon. 9 sides is a nonagon. 10 sides is a decagon. There is a word for 11 side. I believe it's like an ungon or something. We'd have to look that up. And then my 12 sides is a dodecagon. All the other sides do have names. So if you have a favorite number and you just want to know what it is, you could Google what do you call a 27-sided polygon, and you'll be able to find what you call that polygon. So whatever your favorite number is, you could go look that up. Okay, but these are the only ones you're going to be asked to know by their name what their sides are. It's just 3, 4, 5, 6, 7, 8, 9, 10, and then 12. We don't use 11 very often, and when we go above 12, rather than memorize those names, we're just going to put an N in place of the number of sides, and then a hyphen followed with gon. So if we have 15 sides, we would call it a 15gon. Okay, so we don't have to worry about memorizing those. The next thing we're going to talk about, and we'll apply it in the next video, is the polygon interior angle sum theorem. And it says the sum of the interior angles in a convex polygon can be found by the sum equals n minus 2 times 180, where n is the number of sides. Okay, and we're going to look and see why exactly that is. So we know that every triangle has 180 degrees in it, right? So if I have 3 sides, I have one triangle, which means I have 180 degrees. But look what happens as soon as I have 4 sides. Okay, pretend I closed that. Okay, think about if I could divide that into the smallest number of triangles as possible, I would just draw a diagonal, right? And now I have 2 triangles, I'm going to abbreviate, which means I have 2 times 180 degrees. Okay, if I have 5 sides, like a little house, how many triangles, what's the minimum of number of triangles I can divide that into? Well, I can draw a line there, and then I can draw a line there, so I'm going to have 3 triangles, and then I'm going to have, so that's going to be 3 times 180. Okay, think about, okay, what would be next? 6 sides, so let's see, when I draw 6 sides, I usually do a line, and then a less than, and a greater than, and then connect. That's just the way that I do that. So if I want to take this and divide this into triangles, I would probably do something like this. Okay, and I would say, okay, 1, 2, 3, 4. 4 triangles is going to be 4 times 180. Okay, well, look at how many sides each one of these has. So when I look, I know my triangle has 3 sides, and I have 1 times 180. A triangle has 4 sides, and I've got 2 times 180. My pentagon has 5 sides, and I've got 3 times 180. My hexagon has 6 sides, and I have 4 times 180. Look at what we have here. I didn't really write it, but we can think of it as 1 times 180. 3, if I take away 2, that becomes 1. I can make 1 triangle when I have 3 sides. 4 becomes 2, 5 becomes 3, 6 becomes 4, and I'm not sure, let's see if I can draw. 7-sided figures are a little weird to try to draw, but let's see if I could do it. We're going to think that like we're going to draw an octagon, but then we're going to go, oops, just kidding, we're going to make that into a point instead. And let's see, if I wanted to say how many triangles can I make on this one, the minimum number of triangles I can make, 1, 2, 3, 4, 5 triangles, so 5 times 180, and that's when I have 7 sides. So notice each time what we're multiplying by 180 is 2 less than the number of sides we have. So look at the formula we're using for my interior angle sum. It's n, which is the number of sides, minus 2 times 180. because it's the number of sides each time, and then 2 less than that. So we're taking away 2, n minus 2 times 180 is going to give me the sum of those angles inside our polygon. Okay, so in the next video we're going to come back and we're going to apply this formula to a hexagon, a 14gon, and then also to these problems down here. All right, so come on back to see how we're going to apply the interior angle sum theorem.